start today's session. We'll start with today's class with a typical graph which probably you have seen before. dE over dx some of you have seen it somewhere, and we'll try to explain this towards the end of the day. Basically, we'll slowly approach this graph. If you do not know, you can wait for some time. I'll start with this one, and this is very much related to the theme of the course, and you will learn more and more as you progress. Okay, but I will not explain anything right now. We'll try to see how it actually comes and what are the basic features associated with this graph. It's so to say called Bragg peak. Okay, we'll come back to this later on. But let's start when we are having these interactions of photons or radiation and charged particles, both light and heavy. We need to go phase by phase. But before going to that, let me introduce something else which is actually required for this kind of explanation. So probably you have already learned about the elementary particles. I'll introduce a little bit so that it is convenient for me to address certain questions. So all of us are familiar with atomic system. We have a nucleus. Nucleus consists of nucleons, protons and neutrons, and they are surrounded by electrons. We'll see some of the structures, how they are helpful to our study today. Okay. Now we all know there is something called de Broglie wavelength, right? So lambda equal to h over p. So this is a famous relation all of us are familiar with. So h equal to the Planck's constant and p is the momentum. Okay. So this is my relation, lambda equal to h over p. Now let me consider a non-relativistic system. For a non-relativistic system, p square by twice m, where p is the momentum and m is the mass of the particle, is simply the energy of the system. So we can convert and write p equal to twice me square root of e. Okay. Once we get this, I rewrite the de Broglie relation. So lambda equal to h over twice me square root. Okay. So as you see that lambda is inversely proportional to the square root of the energy of the particle. That means if I increase the energy, my lambda is going to decrease. This is crucial to so-called going to smaller and smaller distance or going to higher and higher energy. So if you want to increase the energy, you can actually go to smaller and smaller distance. You can identify object to very small distances. So let's look at another relation which is very much used. Let me, those of you come a little bit late, we'll try to address this graph later on in the day. So let me erase for the time being. Some of you might have already seen the resolution in a microscope is this one delta r equal to lambda over sine theta, right? Where theta is the aperture of the microscope. So if I replace this with the lambda that I have already found, so delta r equal to, so for the timing let me just write it here. So like h equal to this one, so p sine theta. If I don't express this, can always I can represent this way. So roughly this is what I can get. Now what it says, suppose two objects are separated by a distance delta r, then this is the resolution given your aperture of the microscope. Okay. So I can give a direct example. Now all of us are familiar with mobile cameras. So when you take a photo for a long object, relatively longer distant object, maybe it is not clearly visible. So what do? We zoom it. We zoom it so that it looks a little bit better. So that means you are increasing the resolution. The same thing is happening here. So whenever you want to see an object to a very, very small distance, or you want to resolve two objects which are very, they are separated by a very small distance, then you need to go to higher and higher energy. This is the principle. Okay. So let's see how it does. Now I have written this delta r equal to h over p sine theta. Sine theta varies within a 0 to 1, right? All of us. So this is a number, by the way. So let me rewrite this in terms of something h by q, where q I called is the momentum transfer. Okay. So this is delta r equal to q, and let me take one specific example. So what we will do, we will actually multiply velocity of light in the numerator and denominator. Okay. And let's take some typical example. Let's say your QC, or the momentum transfer, is something, since I know what is the value of h, if you have forgotten, so your h is something like 6.64 34 joule second. So usually what we do, because it's minus 34 joule second, we'll use something called energy units. So that will be much more convenient, because we can directly convert into the energy whenever it is required. So I'll rewrite this in terms of, suppose I can take, say, h by 2 pi, which is called h cross. So I'm dividing 2 pi here. So the unit is simply 6.588 into 10 to the power minus 25 GeV second. Okay. By now you might be knowing that GeV equal to 10 to the power electron volt. MeV is 10 to the power 6 electron volt. This is giga electron volt. Okay. So I rewrite this in this form, and I know the velocity of light. C, how much is this? C is 3 into 8 meter per second. So I multiplied all of them and then divide by, because as I said that I want, let's say, my momentum transfer, let's say Q equal to 10 GeV. Suppose you are given a beam which has energy of 10 GeV. We want to see to what distance we can resolve two objects. That's the idea. Okay. So once we put all these values, what we will get, if you have Q equal to something like this, the delta R is roughly 10 to the power minus 16 meter. So what it says, if you have a beam which is roughly, let's say, 10 GeV, then you can distinguish two objects which are separated by roughly 10 to the power minus 16 meter. We know that nuclear dimension is 10 to the power minus 15 meter order, Fermi level. So you can actually go a little bit beyond than the nuclear dimension with 10 GeV. With the modern technology, we are able to go much beyond than GeV. Right now, we have created beams of the order of TeV, which is tera electron volt, 10 to the power 12 electron volt. Okay, so that means instead of 10 GeV, if I put here my Q equal to say TeV, obviously you will go at least 3 order of magnitude down. That means you can decipher object to the distance difference of roughly 10 to the power minus 19 or minus 20 meter, which is a very small number in comparison to, you know, the familiar word called nanovolt, which is 10 to the power minus 9. So with the help of high energy probe, we can actually distinguish objects to very smaller distances. So the resolution power is great, and it is all started from this equation. We can actually use our high energy beam to distinguish objects to very small distances. So with this, what happens? Let me just go back in the timeline. So this is the current scenario that we have beams of the order of TeV right now. So this is how we have achieved. But if you go back 100 years back in time, then initially people actually created MEV beams. Okay, so the beams are roughly, let's say, 10 to the power 6 electron volt. So then, can anybody guess what will be roughly the distance that we can probe? Just order of magnitude, looking at the formula that I already mentioned. Suppose your beam energy is something like, let's say, 10 to the power 6 MeV. You will see that obviously it will be less than 10 to the power minus 16, because now I was taking GeV 10 to the power 9, now I am taking 10 to the power 6. So it will be roughly 10 to the power minus 13 meter or so, 3 orders of magnitude difference. Okay, that means we are not able to see even beyond the nuclear dimension. So that is why in the early days, when we used to have beams of the order of MeV level, we are able to see only the atomic structure. We have nucleus, which nucleus consists of protons and neutrons and all these things. So now with higher beam, we are able to probe to very small distance. That's what we find, that inside this protons and neutrons, there are some other objects. They are not the so-called elementary particles. So the protons and neutrons, which you know, which collectively called nucleons, they are not the fundamental particle as we know today. Instead, there are some other particles which are there inside the protons and neutrons, which are essentially called the quarks. So all of us are familiar from our school days. There is something called periodic table of all the elements. Okay, so they are very successful. We understand many things with that. But the modern version of that kind of periodic table is now replaced by what is called the particle content or the elementary particles. So the elementary particles are, let me just write down in a tabular form. This is the up quark, down quark, charm, strange top and bottom. Okay. So these are the 6 quarks that we have found. All of them have been observed so far. So all these 6 quarks can be used to create anything that we know. Okay, whether it is proton, neutron, or any other element that you want to actually create out of these quarks, you can create. So these are the building blocks or the fundamental particles. And the upper row, the electrical charge is 2/3 of electric charge, and this is minus 1/3 electric charge. So we know this much. Apart from this, we also know, which is, these are called quarks. And we have also leptons, electrons, for explaining electron type neutrino, muon, muon type neutrino, and then tau and tau type neutrino. So as I said, the upper row, the quarks are plus 2/3 charge in the electronic charge units. Then you have the down row is minus 1/3. The leptons are minus charge. As you can see, the superscript says minus means minus negatively charged particles. All of them are negatively charged particle, 1 charge. Then we have the corresponding neutrinos here, 0 charge. They are neutral. Okay, so whenever there will be, because I'll be needing some of them, not all of this table, maybe we'll actually need the kind of particle that we'll be using here. Roughly, will not use strange. So maybe this part of the table will be relevant to our discussions. Of course, they are directly involved, but these two will be indirectly involved. What are the particle that we'll be considering? Okay, and rest are like the higher mass objects, which will not come in day-to-day life, so will not actually use this thing. But essentially, these are the building blocks of nature. Anything that you can create, anything that you know, you can create out of all these particles. Okay, and all of them, these are called families: first family, second family, and third family. These are the 3 family of quarks and leptons. They are called. These are leptons, quarks, and all of them are spin half particle. They are fermions. Okay, so this is the particle content. We also have the carrier particles, so to say. We know that there are 4 fundamental interactions. So let me erase this side. We have strong force, then we have electromagnetic, weak force, and gravitation. These are the 4 forces we know. And the modern version of these fundamental forces, these are called and the carrier particles are, so we know that the strong force is mediated by something called gluons, and electromagnetic by so-called photons, then weak by some particle called W plus, W minus, and G0, and this is by graviton. So this strong force and weak force, they are actually short range force, and this is very long range, infinite range, you can say, electromagnetic, and gravitation also is finite, but this particle is not yet found. We know everything about these 3 gluons, photons, and weak bosons. These are called weak bosons, but this hypothetical particle, so-called graviton, is not yet identified. And we will be actually focusing mostly the electromagnetic interaction, to some extent this interaction. As I said, like in this table, we'll be looking into, we'll be only like related in our lecture, this one and these 2 family from the lepton sector. Similarly, mostly we'll be dealing with the electromagnetic interaction and to some extent in the weak interaction. These are the 2 things that we'll do. Now, all of us know that quantum of electromagnetic radiation, these are the photons, they are the carriers of electromagnetic interaction, and we will be actually looking into the interactions of photons and some other particles which are, let me erase this portion by now you have written. So these quarks and leptons that I have written already, if I use the dot end notation, so the proton can be written a combination of UUD and neutron UDD. So they are called baryons or a 3-quark system QQQ. Q is the generic name that I wrote, all the 6 quarks. This Q, all of this can be any of these 6 quarks. But if you take half quark, and d quark, what you create is a proton. And so on and so forth. There are many variants. We will not write them because these are not needed in this course. Similarly, there will be a class of particles called mesons. They are quark and antiquark. I forgot to mention, whenever I mentioned that table, that we have the quarks, 6 quarks, they also have the antiquarks, all of them. Okay, so like up quark, there will be anti-up quark. Like you can have up quark, anti-up quark, and so on and so forth. Down quark, anti-down quark, all of them will come with the anti-quark. So when you have 1 quark out of these 6, you can take any quark you like, and you can take any quark of anti-quark out of Q bar, you will create some kind of a particle which are called mesons. And the most familiar ones are the pi mesons. Okay, so these are the lowest lying mesons. You can create like UD bar, D bar U, UU bar, DD bar, etc., etc. So you can have pi plus, pi minus, pi 0, etc., etc. So these are the pions we have. Similarly, we have other particles like kaon, D meson, B meson, etc., etc. But we will not be dealing with these particles because, as I said, we will be focused only on the first family of quarks. So mostly these things will be required. And you can have other particles, particularly other things that we'll be considering, like say alpha particle, heavy ions, etc., etc. But inside any element, as you know that there will be only protons and neutrons. So the moment you know proton and neutron, you know almost everything. Okay, so let's not go into that aspect of it. Maybe this much of introduction to the kind of particles that we'll be dealing here will be more than enough. Okay, before I forget to move on, there is something called Higgs boson, which will be connecting to all of them, which will give mass to this one, but we will not discuss anything, but just on passing, let me just mention there is something called Higgs boson. And as I said that the quarks and leptons are basically the fermions, spin-up particles. These are the bosons basically. They are not fermions. Okay. So one important property which we might require is that you already saw that there is something called anti-quark. So you have a quark or a particle, there will be a corresponding antiparticle possible. And we have that thing which was evident when we actually learned what is called the Dirac equation. This is the relativistic equation, not like the non-relativistic equation that we know, which is the Schrodinger equation. Similar to that, we will have Dirac equation. One of the consequences will be you have a particle, then there will be antiparticle. So you have quark and antiquark will constitute antiparticle, and so on and so forth. So this is actually valid for the spin half particles, which is a fermion that I already mentioned. Okay, because one of the particles that I mentioned in the table was electron, if you remember. All we are familiar with electron. The antiparticle of electron is a positron, which has found in recent times lot of application in the form of positron emission tomography. So you cannot have that equipment or diagnosis without having this positron. And positron is an antiparticle. So the moment it was discovered, we found something new which says something about the antiparticle. Okay, but we will not go into that aspect of it, because you will be at some point come across PET, which is directly related to an antiparticle positron emission tomography. Okay, so these are some of the things which you will borrow from the particle sector, whatever basic things that I mentioned at the beginning. So this will be enough for us, at least for the time being. Okay, so let's move ahead. So what we'll do, we'll try to look at and learn the interaction of photons and charged particles. So we'll go one by one. We'll start with the interaction of photons with some medium, and you will, in the following classes, in the next few days, you will learn a lot of things related to the interactions of photons. So here what we'll do, so when a photon interacts with a medium, suppose for some, like in some mechanism, we can create a photon, let's say, somewhere here. Let me change the. And what we see is somewhere here, let's say, this is, so you have this is a kind of bubble chamber where we can see some kind of a tracks of charge particle. This is electron, this is positron. So there is some magnetic field, and they are actually and certainly with reduced radius, and finally they are actually like depositing all energy, and they keep tracks like electron and positron. So I can extrapolate this in terms of some particle which was produced here, because I know some beam was here, and I can see tracks at, suppose a beam was created at A, and we started seeing the tracks of the charged particle somewhere at B. So I am just extrapolated. I assume that a photon has come up to this point, and here actually it is dissociated to a electron and positron pair. So photon, the photon that we learned, which is the carrier of electromagnetic interaction, it has actually converted to a electron and positron pair, something called a pair production. Okay, I will use some kind of a, maybe I can just, let's say you have a photon and then an electron. So this is what is called a Feynman diagram, which I will not explain here, but this is a photon which is going here, and then it actually produces an electron, E plus E minus, let's say, and this is electron, let's say, sorry, let me just put it this way, positron, this is electron, and this is again a photon. This is some nucleus, let's say. Okay, so whatever I have written here in a modern language and picture form, I have expressed the same thing. I will not explain this how it happens, but this is essentially the diagram that we found, that there are some beam or photon created here, and it passed to a certain point, and there in the material medium or some kind of a medium, actually it interacted. You can see that here I have written some kind of a nucleus actually So if you want to use some energy momentum conservation relation, something is violated here. You cannot have one photon going to two E particle. Okay, you need to have some kind of a material medium, or two photon can go to this one also. That's what we have used a material medium. Okay, so in presence of some medium, the photon actually dissociates to particle and antiparticle. So this is the track that we have found, and this is one kind of evidence that a photon actually dissociates to the particle and antiparticle. Okay, now we will see what are the possible interactions we can have in case of photons. So let me explain before going to that one. All of us are familiar with Rutherford scattering, right? You have alpha particle bombarded in some kind of a atomic target. We find that there are scattering. Okay, so that leads to some kind of a scattering cross section, d sigma Rutherford by d omega, which is roughly equal to z square, then alpha square 4e square 1 over sine 4 theta by 2, where this alpha characterizes the electromagnetic interaction and E is the energy of the beam that was the target, basically, sorry, the beam which was probed, and Z is the Z square alpha square. Z is the atomic number of the target, and theta is the angle of deflection. So what we do usually, you have some kind of a target, let's say, and you hit with some kind of particle, let's say particle of mass m1 and v1, let's say this is at rest, v2 equal to 0. So before the collision, you hit some particle like this and use energy momentum conservation. Maybe after some time what will happen, suppose instead of making a broad target, let me say there is some target here. So actually maybe the target is shifted or displaced and another particle goes this way. So you can have, let's say, m2 v2, so m3 v3 and let's say m4 v4. So use the kinematics energy momentum conservation law to find out the dynamics. So this is what we'll do. We cannot use all of the tricks here, but this is the basic mechanism that we'll be using. Another thing we'll actually use during our lectures is similar to what I just mentioned. Suppose you have an atomic electron which is associated to some kind of nucleus. Suppose you have suppose this is the radius at which from the nucleus the electron orbit is. Let's say this is A. And I have a beam which actually, say, let's say electron, which is actually moving in this direction. And suppose this is what is called the impact parameter, which I think you are familiar with from your classical mechanics classes. So the closest distance to the target, let's say this is my B. And suppose the impact parameter B is roughly equal to A. Then what we call is a hard collision. Now suppose your B in a different case, let's say same target, let's say A, but your B is such that B is very large. That means B is much greater than A, then this is called a soft collision. Okay. There can be another possibility in between these two. So this is again A, but so the B is now very less. It goes very close to the nucleus. So B is much less than A. This is what is called radiation collision. Okay. We'll come back to this because this is one of the applications that we'll do, and most of the time you will be actually doing mostly at this level or this level. Either it is a hard collision or a soft collision. It could be like this also once in a while, not all the time. Okay, so these are the three possibilities or possible situations that will come across while discussing the subject that we have right now. Okay, so going forward, we have mostly the photoelectric effect. When a photon interacts with any medium, these are the three prominent processes that can take place. Compton effect or Compton scattering, production. Of course, there are others. For example, Thomson scattering. There can be Thomson scattering, Rayleigh scattering, there will be Bremsstrahlung processes. So I'll come back to Bremsstrahlung. I may not discuss too much about Thomson and Rayleigh scattering, but I'll comment right now, right away, so that we can focus on the other aspects. Okay. So whenever a classical electromagnetic wave or photon actually hits a electron target, then you have this Thomson scattering. And I'll just illustrate the scattering cross section. T corresponds to Thomson. So sigma T is something like 8 pi by 3 the classical electron radius r square, where r is nothing but our electron is e square over 4 pi epsilon 0. Then you have mc square. M is the mass of the electron, or mc square is nothing but the rest mass energy of electron, you can say. And charge of the electron is known. We know these are numbers, and then this is also fixed. We know the before we move, we know that the rest mass of electron is something like 0.511 or 51 MeV. So we know the Re square is something like, let's say the value is almost fixed, so 2.8 into 10 to the power minus 15 meter. So we can find out the Thomson scattering using this very simple formula. And similar to Thomson scattering, we also have Rayleigh scattering, where there will be some kind of a region R scattering possible. But I will just illustrate one formula related to one specific case, which is similar to the Thomson scattering, because these are the possible effects one will have photon when interacts with electron in the medium. So sigma r simply equal to sigma t lambda to the power minus 4. So the blue sky is explained by the Rayleigh scattering. Okay, so I will not discuss more because they are not that much significant in comparison to these three processes. So we'll focus with the photoelectric effect first and then proceed further. So photoelectric effect, all of you have studied it many times before. So we'll not go into those aspects of photoelectric effect that you have studied, but rather focus that why it is very much relevant in the medical sector. Okay. So what happens in the photoelectric effect, we'll see, and then maybe we can conclude more from there. So let's say you have, so let me write what is suppose when a photon, it's a atomic system, let's say some absorbed medium, what happens? Something comes out, right? Anything knows what comes out? An electron comes out. Okay. So if the photon interacts with the medium, then there is a possibility that an electron will come out, which is what the photoelectric effect is. Can anything else come out of this kind of possible interactions? So whenever I write this curvy line, this corresponds to a photon. Anything else which can come out in this kind of specific processes? Sorry? Gamma rays can also come, right? We'll see how it comes. Okay. Okay, so before we see that, let me just illustrate that a photon hits a target. Maybe this is my target, whatever observing medium that we have. There is a possibility that there will be no interaction. Photon will not give anything, it will just pass. Okay, so this is one possibility, there is no interaction, so that photon just passes through it. Okay, so no interaction. One process is our photoelectric effect. So maybe an electron comes out. Okay, so this is one is our photoelectric effect. Or you can have what else you have? The second process. So you have photon, and then the photon comes out. Or you can also have, maybe right on the top, the fourth case, let's say, there will be a photon, but it's a different kind of photon with a specific energy, 511. Okay? EB or MEB? Sorry? KEB. Okay. Or 0.5 MeV. So this is what is called pair production. Okay. Sorry, this is what is called? Sorry. Pair. So that's what I will just write. It's a maybe. Instead of photon, I'll write an electron and positron. Okay, so
It should also be positron. Huh?
so obviously there will be a positron, but I just write one of them. The characteristic same energy, 511. Okay, so these are the possible process that can happen. Now, out of the possible radiations that we have, so-called alpha, beta, and gamma, if there is some alpha particle is emitted, then one can stop this using just a paper maybe. Okay, you don't have to do too much. You can actually place a paper, you can stop an alpha particle. Okay, and if you want to stop a beta particle, maybe you need something else. What you can do, maybe let's say thin aluminum sheet, will be okay. Beta minus is your electron that we know. This is a beta particle, electron basically. And if it is photon or gamma, then so this will not be stopped in paper or aluminum, then you need something special. You need lead, let's say. You need lead to control photon. Of course, I will not discuss about neutron, which is even more dangerous, depending upon what is the energy. So it will not be stopped in even lead also. You have to make a good concrete, high, thick concrete wall to stop neutrons. Okay. So neutral particle, basically, it doesn't do too much of interaction. But we will not discuss about neutrons, but this can be stopped with this one. And typically, the alpha particle can go few centimeters and can be stopped as such. And the beta particle can be up to, let's say, few meter in air, it can go to few meters, let's say. This is few centimeter. Gamma, actually, if it interacts, then it stops. If it doesn't interact, it goes infinitely. Okay, so there is, it's supposed to be infinite range, but if it makes some interaction, we'll see, it will be absorbed completely, or otherwise it just passes. And neutron can be. So these are the kind of, since neutron hardly interacts, so we'll not have the analogy here right now, but this can be stopped wherever you want. You want a good shielding to have these radiations controlled. Okay, so let's look at the mechanism of photoelectric effect then. Let's come to the idea. Suppose you have a nucleus. You have K cell, you have L cell, any specific nucleus. So suppose you have, we know that in K cell you have 2 electrons. Now when a photon hits an electron in the K cell, it knocks out the electron. So once it knocks out, let's say there is a hole here now. So the electron, let's say, goes out. Okay. So this is my K cell. So the moment there is a vacancy in K cell, then electron from higher cell will jump to this K cell. So suppose an electron from this cell jumps to this one, then the energy difference between these two will be is what is this radius called? Gamma. These are X-rays. These are characteristic X-rays because we know the energy level of K, and this, the binding energy difference will be actually X-ray. So these are X-ray emission. So along with electron, you will have a characteristics X-rays. Okay, this is one possibility. There is a possibility that this energy difference is actually, instead of X-ray, there will be a secondary electron which will be coming out of this one. Have you heard of something called Auger electron? So instead of this X-ray, you can also have, this is relatively lower in comparison to the traditional X-ray, characteristic X-rays basically. So X-rays will depend on from which level it has come, like K or L, depending upon K alpha, K beta, etc., etc. But the Auger electron will be, instead of this X-ray, there is a possibility of secondary Auger electrons which will be coming out of this process. Okay, so the beautiful part of this gamma radiation is that, as you notice, that it is very difficult to contain these high power gamma rays, but nature has given us some kind of a beautiful kind of process in the form of photoelectric effect, that when a photon interacts with some kind of material medium, there is a possibility that it will be completely absorbed and then an electron will come out. These are relatively less dangerous than the high energy gamma rays. Okay, so the moment you have these electrons, we know that it's relatively easy to control the electron rather than controlling the photons. So the photons is absorbed, and then electron comes out, and then life becomes a little bit easier because we can control electrons very easily rather than controlling the photons. Okay, so but there is no guarantee that it will make an interaction with specific process like here we have in the photoelectric effect. So that is how it is. Okay, so it so happens that one can actually find out the cross section for photoelectric effect, which I will not do here. But before we move forward, I think all of us are familiar with this formula, right? Kinetic energy of electron, let's say, which comes out from this process. What is that? Suppose h nu is the energy of the initial photon, and this is the work function, let's say, phi or w, whatever notation you want to give. So this will be the energy difference that will be actually carried by the electron. Okay. So this is very well known, and all other properties I will not discuss here. We will just focus into the basic difference that we have. Now mostly what happens, the photon energy, what is the energy of the photon that determines which cell it will make interaction. Okay, so if I write the cross section for photon, which I will just quote here, let me erase this portion. So this is this axis is basically the attenuation constant in the y-axis, and the x-axis is the energy of the photon. Then what will happen? Okay, so I'll before that let me write the cross-section formula. So the cross-section formula for photon actually is something like 4 alpha 4 z to the power 5. I'll explain this, and this is the phi t and mc square over h nu to the power 7/2. So let me explain. So this is the cross section of photon interacting with some medium, where the medium has the atomic number as z. Whatever is the z value, you can consider any element that you like. Corresponding z will be there, and z to the power 5 will appear. Alpha I have already used. I didn't mention what alpha is. I think all of you know what is alpha. Alpha is the fine structure constant 1 over 137 that you use in Bohr model. Okay, so E square over 4 pi, which is alpha, and 1 over 137, that is alpha to the power 4 sitting here, and z is the atomic number of the medium that we are considering, and phi t is the cross section I just mentioned at the beginning. What was that? Thomson cross section. That was the Thomson cross section. What was that? 8 pi over 3 re square. This phi t. So you have alpha to the power 4, z to the power 5, phi t, and then you have this is mc square by h nu. So one of them is the photon energy, and this is the rest mass of electron energy basically, to the power 7/2. So this is for a very heavy element where z is very large. Then you can see that if you compare this photo cross section for a light z material and a heavy z material, you can see that huge difference because of z to the power 4. All others will same, alpha is same, this will be same, energy will be maybe different, or if you consider the same energy for different material, then there will be a factor of z to the power 5. For low element, let's say z equal to 5 or 6, it will be very small, and if you are considering something like z equal to 80 or 90, to the power 5 will be a huge enhancement factor for this. Okay, so you can have, if you consider the high z material, then the cross section will be huge here. But remember, there is one factor which is energy to the power 7 by 2. Or this is, so these are the two striking factor. Alpha is a constant, so this is the value. We are not bothered because that will be common in all processes. All specific photoelectric cross section. But here you have z to the power 5, and this is roughly e raised to the power minus 7 by 2. So z to the power 5 and e raised to the power minus 3.5, let's say, or 7 by 2. Okay, so this is how the cross section will behave. Now let me just plot here, which I already wrote some time ago. So this is attenuation coefficient. Let's say, let's scale it. Let's say this is 1 keV, this is 10, this is 100, and so on and so forth. Let's say 10 MeV. Now what will happen? Let's say here I can have 10,000 and so on and so forth. This is 1,000, 100 and so forth. So you will have something like, let's say, so something like this. So this is the energy in MeV, photon energy, keV or MeV, let's say EV, because I have written keV also in electron volt units, let's say. Now you can see here there is a kind of a edge. So this is the K edge. If you zoom this sector, for example, you just increase the x-axis, you can see also L edges here. If you zoom this person, you will see that there will be L edges also at this point, which will be for very low energy photons, not very high energy. Okay, so that will be possible when your photon energy is very less. Now the typical part of this one is that you know that this energy level have some specific value, binding energy, all levels. So the closest one to the nucleus, KSL, will have the maximum one. So if you want to actually knock out the KSL electron, so you should have the maximum possible energy. Until and unless the photon doesn't have that much of energy, it cannot actually knock out the K electron. And before that, it can actually knock out the lighter energy, basically relatively free, you can say L or M. But the most important of them was the K as electron, for which you need high energy photons. Okay, so this way you can actually have an electron and then characteristic X-rays, and also you can have a possible secondary Auger electrons also in this process. Okay, so we will continue with this kind of explanation, and I will come back to that one in the next class. Maybe I will introduce just now, and we will continue. This figure actually is a building figure. We will actually go one by one, superimposing on this. Let me just superimpose the picture of Compton effect here. Since Compton effect is very well known, so let me just superimpose the Compton effect and then I'll explain. So maybe this is just 1, let's say. This is 10. So it will be maybe this is a little bit more. So after, if the energy of the photon is more than say few keV, let's say this is in keV, right? keV. So maybe around 100 or so, and more than that, then it will be dominated by the Compton effect. Okay, and we'll see, maybe we'll see more on Compton effect, but maybe here I will stop. So we'll explain actually this graph the next class. Okay, so let's stop for the time being.